Statistical significance in hypothesis testing. Let's say you started taking vitamin D a couple of weeks ago and you notice it takes you less time to fall asleep at night. Is this a result of the vitamin D or is it something else? Is there maybe something else that causes you to fall asleep more easily? Being a good citizen, you decide to do an experiment. You take 50 co-worker volunteers and you split them into two groups. 125 co-worker groups will get vitamin D, the same one that you have taken, while the other group will take only a placebo. You notice that the guys who took the real vitamin did get a shorter amount of time to fall to sleep. Was it the vitamin D as the cause? It could be the case, but it could also not be the case, because maybe if you have taken these 25 people, 25 co-workers, and just did a snapshot experiment, you would find that at one time they have shorter amount of time for them to get to sleep, and at another time it takes them more. There are external reasons, it's just random, and you can just not deduce from the vitamin D because it would happen anyway, even if you did not give them the vitamin D. You did not do this experiment in a specific parallel world where you did not give them the vitamin D. You did the experiment on two groups, and those two groups have separate time. And if you repeat it on the same group, you would do this on a separate time. So it is not a pure experiment. Okay, this experiment was cluttered by reality, so you don't really know if the result means that the vitamin D has affected this group or not. And this is where hypothesis testing and significance in hypothesis testing come into place. They are there to help you to assess whether your results are significant, so you can deduce some causal effect in between the pill and not taking the pill. Hypothesis testing is almost what we did here with the experiment, but we want to also know, was the vitamin D correlated to the change in the sleep behavior or not? Basically, we want to answer the following question. We want to calculate how unlikely was it for the sleep pattern to change, or was it likely for the sleep pattern to change in any way? And if sleep patterns change in any way, then we cannot really explain it by the vitamin D because they are changing in any way. Or at least the results that we had were not significant enough. Because if sleep patterns change from time to time for our workers, then it's not that of strange thing that it changed while taking the vitamin D. In other words, it's just a thing that happens. We have two ways to estimate whether the change was random or not. The first thing that we check with significance testing is to check how much did the sleep pattern change. Did they move from 30 minutes to fall to sleep into 30 seconds? Because if that's the case, then we might be able to, hey, we have here something because this change was huge. If it was only from 30 minutes into 29 minutes, then this could well be a random thing. It's not that significant. So the higher the change, then we say that the more significant it is. And we would give this significant a higher number. So we want our formula to reflect this change. When you would look at the formulas for the significance, then you would see that the higher the change from the original value, then the higher the significance is. And this is the first part of significant testing, checking how much change did we have. The higher, then the significance would be higher and you would see it in the formulas. The second thing that we are going to check in order to estimate whether this change was just due to random stuff going on in their life, or could it be related to actually the pill that we gave them, is whether the set of results that we got from them is very diversified or not. For example, if all of them reduce the time to sleep in exactly X minutes, all of them, then we have no variance in our results. So this could not be just a random things. We are highly suspicious on the pills that we gave them. However, if one guy reduced it by 1 second and another one reduced the time to sleep by 29 minutes, and for the third it even raised above 30 minutes, then we have a lot of variance in our results. Therefore, it's less likely that we can deduce anything about the pill with strong significance. Therefore, we have two items that we measure in order to check whether we can make any claims about the hypothesis. How far is our average value from the original average value that we had? The farther, the more effect we got, and more significant it is. The second thing that we check, and we have it in the formulas for the significance, is how variant our measurements, not exactly the measurements, we'll talk about it a bit later, but how variant our measurements are with relation to one to another. So that the more diversified the results, then the less we can say that they are significant. So if you look at how we check for whether we can make any claims on our hypothesis with high significance, what we are doing is looking at the results we got. We then compare them to the original results and see how far are they and how spread the results themselves are. However, I skipped here something very important which I didn't tell you yet in order not to overcomplex things, but now that we understand that we have both the average and the variance to check for significance, let's move ahead. This new thing stands at the basics of significance check. When we look at the standard variation of our data, we don't just look at the standard variation of it, we look at the standard variation of the average value of all our measurements. So we look at the standard deviation of the average of the measurements and not the measurement. Why is that? Why do we care so much about the average of the measurements and less about the measurements themselves when we check for significance? This is because it was proven, and you can also intuitively see that the standard deviation of the mean decreases when we have more measurements. Let's discuss this a little bit more. In general, it does not matter the source of the distribution of the measurements that you have, because when you check the average of the measurements, the source distribution does not matter. You would always get in the average of the measurements a normal distribution. Let's take an example. If you toss a coin, and let's call the heads 1 and the tails 0, then if you toss it 10 times, then the chances of getting head or tail is 0.5 for each coin toss. It's uniform. However, if you toss a coin 2 times and then sum the results and then toss the coins another 2 times and sum again the results, then we have a few possibilities. We could have 0, 1, and 2. If we repeat this for 10 experiments, then we could count the sum of these experiments, of these 2 toss coins experiments, and could get different values. If we look at the average of these experiments, we would get a normal distribution. But if you look at each separate experiment, it could be either 0 or 1, and it would be a uniform distribution. Because we have higher combinations. We have higher combinations for the center. We could get 7 plus 3. Okay, we could get 2 plus 8. All of them are equal 10. But in each toss of a coin, you get only 0 or 1. You don't have these combinations, which make it a normal distribution. So now that we know that our averages behave in a specific distribution form in the normal distribution, we can look at the results and we know it's coming from the normal distribution. So we can deduce stuff on it. We can tell, hey, this result was really of the normal distribution curve. There was so much little chance this should have happened when we look at the distribution curve and when we look at our results. So this must be significant. To sum up, the significance is a number. We calculate this number with formulas. However, there is an intuition. When you look at any of these statistical formulas that compute the significance of our experiment results, you would always see that what they do is check how different are the averages that we got in the experiments, how different are these averages from the population average. If we know it, the higher this difference, then the more significant this result is for us. However, the higher the variation of the averages of the measurements of our experiments, this means that our sample results are not stable. And because they are not so stable, then it's hard to conclude any conclusions about the experiments. And therefore, we have a lower significance. So I hope this gave you some intuition, because when you look at the formulas for the significance, you would see this very same concept. You would see that we compare the average that we got from the original average, and then the higher it is, the higher the significance. And you see that we divide by the standard variation of the averages, because the higher this one is, then the lower our significance is. And that's the whole point of these formulas. So there are multiple formulas and multiple ways to check things, whether you have the population mean or you don't have it. But this is the core concept. I would say this is the single most important core concept about hypothesis testing and significance.